I can't remember precisely in which book of Stuart Kaufman, whether it was Investigations from 2000 or Reinventing the Sacred from 2004. He writes about the problem of relating matter, energy, and information. In the sense that traditional science, reductionist science, has assumed that the real phenomena in the world are described by physics, matter and energy, and then everything else is derived from it, independently of whether we consider biological phenomena and social phenomena as real or just epiphenomena. Many efforts have tried to reduce everything, all phenomena, to physics. Of course, we have mentioned the problems that this worldview has. Also assuming, first of all, assuming that there is like a elementary level, and I mean, it seems that elementary particles, we're not sure that we cannot divide them, just we don't have enough energy, other hand, to be able to smash them and break them and detect what's left. But let's say they're finding more and more details about elementary particles, so it's not trivial to say, okay, now once we understand elementary particles properly, we will be able to understand everything else. And on the other hand, even if we do, because of complexity, even if you know everything about elementary particles, that doesn't tell you everything about atomic physics and molecular dynamics and biology and so on. So traditionally, in spite of these limitations, traditionally people have tried to describe information in terms of physics. And this has been a big problem because there's a gap between biological systems that we can agree that they process information. I mean, there is meaning in the goals of living organisms. We can try to discuss what is the origin of goal-directed behavior, but we can describe bacterium swimming in a glucose gradient as having a meaning, basically something positive that will nurture the bacterium. Of course, it not will be the same meaning as humans might have, but it's something that guides their behavior. And the same problem with intelligence or cognition or minds. Let's say this led Descartes to propose dualism, like there's res extensa, which is the physical world, including animals, and then there's res cogitans, which is a human mind, and it's kind of independent. So he was suggesting that it cannot be reduced, and many other people have tried to reduce human intelligence to physics, and but I mean, all these attempts have failed. So we can explore the other way around. Instead of trying to describe information in terms of matter and energy, let's describe matter and energy in terms of information. Like this, we can derive lots of information and try to describe all phenomena in terms of this. So, a caveat, we are not speaking about ontology. So in philosophy, ontology is the study of things independently of one observer. Sorry, things themselves or things as they are. We're speaking about epistemology, which is descriptions of phenomena, how we get to know phenomena around us. So when I speak about the world as information, it's not that, let's say, saying that atoms ontologically are information, but atoms can be described as information. And then we can explore what's the usefulness of having this description. And descriptions do not change phenomena that they are describing. They're just useful or not, depending on a specific context. And also, we can have different descriptions of the same phenomena, and they're not necessarily contradictory, because unless we are Platonists, we can accept more than one description for the same phenomena, and we don't assume that there's only one true description and all the others are mistaken. So we can give a notion of information, anything that an agent can perceive or sense. This is in line with Shannon's notion of information, which can be seen as just an arrangement, a structure or organization as opposed to randomness. You can measure it in bits. You can apply information as a descriptor to everything that's around us, because it's basically, if you cannot describe it, then you cannot say much about it. And if you can describe it, then that description is already information. So it applies to everything that you can describe. So particle, wave systems, networks, agents, automata, computers, feelings, everything can be described in terms of information. And also, it can be a meta description in the sense that there are several existing theories that are very useful, and then you can describe these as well in terms of information. So it's like an inclusive formalism that contains all others. And then we can describe an agent as a description of an entity that acts on its environment. Agents are also information, but not all information is agents, because not all information acts on its environment. And I mean, there are plenty of examples of agents: humans, cells, molecules, computers, programs, a city, a society, an electron, a market, an institution, an atom, a star. So we as observers can describe each of these as acting in their environment simply because they interact with it. So that gives us enough justification to call them agents. But for example, temperature, color, velocity, hunger, profit, this is information, but this is not agent. These are not agents because they're not acting on their environment. They are not entities. We can define the environment of an agent as all the information that interacts with it. So information can have more than one meaning, and this will be relative to the agent perceiving it. So the same information can acquire different meanings depending on who perceives it or how it is perceived. And I mean, a clear example is the same words that have different meanings in different languages. So depending on how you perceive it or in which context the information is located, it will have different meaning. And we can speak only about information once an agent that can be not necessarily a human perceives or interacts with it. And the meaning of information will be given by the use an agent perceiving makes of it, this following Wittgenstein. In other words, how the agent responds to it. So depending on how an agent changes its behavior in presence of information, then we can interpret as second order observers of that information what's the meaning for that agent of that information. So for example, we can describe electrons as agents that are perceiving other electrons as information. Computation that, I mean, it's central to this course, can be seen simply as a change of information. Difference with matter and energy is that there are no conservation laws in information. I mean, there are conservation of matter, conservation of energy, but there's no conservation of information. You can create it, transform it, or destroy it. And you can see matter and energy as particular types of information where you do have conservation laws. Well, this is important. For example, I think at some point we mentioned that our current economy is based more in information rather than on matter and energy. I mean, in the agricultural age, it had to do more with matter, industrial age more to do with energy, and these were conserved. So let's say the economics that were developed to describe those economic systems, agricultural and industrial, derived conservation of value. but in spite of, let's say, you already had speculation in stock exchanges, like in the well, there are examples of the 18th, 19th century speculations of the stock market. Newton lost, I don't know how much money in the stock market. Made some investments in the West Indies companies, no, the East Indies companies. Well, but anyway, economy uses the tools from physics where you have conservation, but in an economy that is based more on information, and you can see this with music, with videos, with video games, the value of commodity is less and less correlated to the effort or the work required to produce it. So on one hand, this creates billionaires out of thin air, and on the other hand, let's say you can generate wealth out of thin air. And I mean, you could do this before, because I think economy can be better described as information, but there was stronger correlation with matter and energy, that they have conservation, and this is less and less the case. I mean, of course, there are plenty of commodities that have to do with matter and energy, and these are more or less conserved. But the tools of economics should be updated to allow for non-conservation of value. So there's this idea of the arrow of complexity, that since the Big Bang, the complexity in our universe has increased. Basically, first there were simple atoms, then more complex atoms, then molecules, then more complex molecules. And at some point there were some protocells, then cells, then more complex cells, let's say from prokaryotes to eukaryotes, then multicellular organisms, societies, ecosystems, and so on. So there has been an increasing complexity in the sense that in the early universe, there were no biospheres. So let's say there weren't such levels of organization. This is called the arrow of complexity. And one might, well, the question is why this has occurred, and how this has occurred. I mean, it can be easy to explain, okay, if you start from Big Bang, you cannot have this organization, but then how do you get the increased complexity that we observe, and what's its tendency towards the future? And so if we start exploring laws of information that apply not only to matter and energy, then we can understand better the nature of the evolution of complexity, and under which conditions it increases, under which conditions it doesn't increase, and what are the mechanisms for achieving this. Elio asks, the dimensions of systems is matter, space, time, energy, and information. It depends on your description, because, for example, perhaps you know about the Wolfram Physics project. They start just with space, and then they derive everything from that. According to Buddhist philosophy, space is information, so it's kind of coinciding with that. So in the context of this talk, you can see everything in terms of information. So space, matter, energy, time, there are types of information. But here I'm not looking at the, let's say, substrate of that information. That, I mean, you might argue that, okay, but where do you store that information? And you need physics for that, of course. It's not like information is just somewhere, and then out of thin air, matter arises. I mean, the laws of matter are there. It's just that for the purposes of studying the evolution of complexity, it can be useful to describe the loss of information, to describe how it has increased. But it doesn't matter that the laws of physics are wrong or invalid. It's just for this particular context. So these tentative laws of information should be applicable to everything that we can perceive. They're a generalization of universal Darwinism, and the generalized Darwinian cybernetic thermodynamic and complexity principles so far are tentative. So let's say it's useful to criticize them and see what flaws and drawbacks they might have. So the first is the law of information transformation that basically says information will potentially be transformed as different agents perceive and interact with it. So I should say these laws could be also called the tautologies of information because they are so basic that, let's say, it's difficult to argue against them. But then the question is how useful they are if they are tautologies. No? But I think they're useful for the reasons that you will see in a moment. So this law of information transformation basically says that change happens, or in other words, computation is going on. This can be seen as a generalization of random variation of biological evolution, but it applies at all scales and it ensures novelty. And throughout evolution, the transformation of information will generate a variety or a diversity, and this can be used by agents for new purposes. So one example is RNA polymerase that copies DNA sequences, and there's a copying error, and suddenly you have a new sequence, and you can codify a new protein, can have new functionality, or you can lose all functionality, and this is novelty, and evolution can work with that. So we can classify different types of information transformation. One, which I call dynamic, is when information changes itself. You can consider this as objective internal change. So you have some information and then that information changes. Static transformation would be when the information doesn't change, but the agent perceiving that information changes. So there's a dynamic change, but in the agent's information. So you can consider this as a subjective internal change. Then you can also describe active transformation, and it's when an agent acts on its environment and transforms that information. And you can consider that as an objective external change. Stigmergic, like with social insects, an agent makes an active change of information, which changes the perception of that information by another agent. So you can consider that as subjective external or intersubjective change. Then second law is the law of information propagation. And it says that information propagates as fast as possible. And I mean, we have to explain what do I mean by as fast as possible. Well, we can say that different information will have different ability to propagate, in other words, a fitness. And then since you have variety because of information transformation, there will be some information that will be more or less capable to propagate than others in a specific context. So this is a generalization of natural selection, the maximum entropy production principle, the second law of thermodynamics, Hoffman's tentative fourth law of thermodynamics. And there are several examples. So in thermodynamics, you can say that molecules transmit information when they try to reach equilibrium, maximizing entropy. In life, genetic information and in culture, information is propagated among individuals. And it's interesting that phenomena that normally are considered opposites. So in thermodynamics, entropy increases. In life, entropy, is more or less maintained because you don't have minimal entropy either, but let's say it's not maximum entropy. But let's say many people describe life as fighting against entropy. But if you consider information that is fit to propagate at different scales, then at the thermodynamic scale, high entropy information will be fitter than lower entropy information, and that's why, let's say, thermodynamic systems tend to high entropy state. And in living systems, that's not the case, but let's say in terms of entropy, but it is the case in terms of information, in the sense that the fitter information for living systems doesn't have a high entropy. So the same law comprehends both cases. So we can also identify different types of information propagation. Autonomous information propagates by itself. I mean, no information is isolated, and also at least some information is determined by environment. But if more information is produced by itself than by its environment, we can call this autonomous propagation, and actually you can measure this. Symbiotic propagation would be when different information cooperates and they help propagate each other. You can speak about parasitic information when some information exploits other information for its own propagation, or altruistic when some information promotes the propagation of other information at the cost of its own propagation. So, of course, the terminology has strong influence in biology, and in biology you can clearly see these examples, but you can also see it in all phenomena, that you can find examples of these different types of information propagation. The law of requisite complexity generalizes Ashby's law of requisite variety. So if we have transformation of information, we will have a variety of complexities, but then more complex information, the information transformation will produce some information with higher variety and some information with lower variety. So then for the information with higher variety to propagate as fast as possible, it will require more complex agents to perceive it, to act on it, and to propagate. So just like Ashby's law of requisite variety tells us that a controller requires more variety than which is trying to control, an agent requires at least as much complexity as the complexity of the information is trying to propagate. So an agent cannot perceive and thus contain information more complex than itself. So we can use this simple, almost tautology to explain the error of complexity as a drift, in the sense that you simply have a variety of complexities, of information with different complexities, and then the agents that interact with that information will be triggered to interact and to develop higher complexities as well, because of that variety. So basically that drift will fill with time throughout evolution the niches for higher complexity. So an example, complex proteins will require more complex RNA to propagate them. Law of information criticality tells us that transforming and propagating information will tend to a critical balance between its stability and its variability. So we already mentioned that if you have information that is too stable or ordered, let's say order dynamics, then this cannot propagate. If you have chaotic dynamics or highly entropic information, this will also have more difficulty propagating. So on the one hand, you have the extreme of information that propagates itself, tries to maintain itself as much as possible. So that would be robustness or order. But transforming information will be varying as much as possible. That would be adaptivity or chaos. So critical information will be a balance between these two and will propagate better than a stable or variable one. And this is why this law of information propagation says that information spreads as fast as possible. So it's kind of two sides of the same coin. So this generalization of the age of chaos, self-organized criticality, complexity from noise principle, also could generalize Kaufman's four candidate laws for the co-construction of the biosphere. And I think I mentioned briefly that we have some ongoing work where we are finding that heterogeneity promotes criticality in complex systems. So with random Boolean networks, we already saw how this works. The law of information organization tells us that information produces constraints that regulate information production. So these constraints can be seen as information, as Kaufman was proposing in his investigations. And we can say that evolving information will self-organize by transformation and propagation to regulate information production. And basically, this can be seen as information as having a certain control over its environment. So the example of a cell with producing its own boundaries. These boundaries are basically an organization or a structure that preserves the organization of the cell itself. So yeah, the life would be the characteristic example of this, but the same applies to nations, to ideologies, to fads, to memes. I mean, you can see that many types of information generate their own constraints that will facilitate their propagation and their production as well. And from there, very similar information self-organization, we can say that information tends to its preferred most probable state. This is a plain tautology because we define probabilities precisely in this way. So it basically says systems tend to the more probable state. That is a tautology because that's how you define probabilities. And Ashby already told that you can describe dynamical systems with attractors as self-organizing because their dynamics organize into the attractors. And it's related to information propagation in the sense that preferred states are those that are propagated. And this basically tells us that not all states are equal, and therefore that will lead to self-organization, and pattern formation is one example, but we see self-organization also at all scales. The law of information potentiality tells us that an agent can give different potential meanings to information. So this is related to the passive information transformation. So the same information can have different meanings. This is polysemy, or different information can acquire the same meaning, homonymy. Yeah, I mean, this basically says that the meaning of information is not fixed. The law of information perception says that the meaning of information is unique for an agent perceiving it in unique, always changing open context. So different agents, contexts, and levels of detail will give different perceptions of information. This gives always a space for novelty. This is also related to the passive information transformation, but also to information propagation because the preferred states are those that are propagated. And there is a so-called first law of human perception, which tells us whatever is perceived can be perceived only from a uniquely situated place in the overall structure of points of view. This basically says that if you go into the highest level of detail, then nothing repeats, then everything is unique. And this gives you always a space for novelty. I mean, nothing will be repeated. Of course, we generalize, we make abstractions, and then we can apply the same categories to different situations. But then if we increase the level of detail, then we will always have unique information, and then we can exploit that unique information with different purposes. So we can speak about different scales of information perception. So the same information can be perceived at different scales. So if we increase the detail, the information will tend to infinite because we will be describing elementary particle by elementary particle, and they will change constantly and they will never repeat themselves. But then when we increase the scale of description, there will be less distinctions, and therefore we require less information to describe that phenomenon. So if we increase the scale all the way to infinite, then the information required to describe that scale will tend to zero, because everything is contained. So in Buddhist philosophy, this is also known as the highest view, and there's no right or wrong because there are no distinctions. And when you contain everything, that leads to bliss. That is permanent, yeah, because it doesn't depend on the changes that occur with, let's say, at lower scales of description. And then following the law of information criticality, agents will tend to a balance of scales, trying to predict most with the least information. Because of course we can say, well, if we can describe the same phenomena with different scales or different amounts of information, which one is the best? And let's say we can assume that there is no a single best, but it depends also on the purposes. But basically, how much can you predict with the least information? So you want to have very few information that gives you lots of predictive power, and that will give you the appropriate information scale. And then we can use this to discuss the notion of life. I mean, there is no agreed definition of what life is. And because of that, it's difficult to study the origins of life. So if you don't have a proper definition of life, then it's very difficult to say how life arose, because some people will, I mean, there's not like a ruler and then you say, okay, here is 0 and then here is 1, there life arose. And there are many concepts that have been proposed: autopoiesis, autonomy, individuality, agency, goal-directedness, purposefulness, and so on, that are related to living systems. But what we can say is that we need to abandon a sharp distinction between life and non-life, in the sense that it's not useful to study the origins of life, like, okay, there's a threshold and before that there's no life and suddenly there is life. But since life is very complex phenomenon and it requires several ingredients, most probably you didn't get all of those ingredients at the same time. So in order to describe the origin of life and the evolution of life, you need a more gradual notion of life. And one way of doing this is with the so-called life ratio, which is the ratio of information produced by itself over the information produced by its environment. So basically, a system with a high life ratio produces more of its information than the one it receives from its environment. In other words, it produces more of its own constraints than the constraints that are produced by its environment. So this is also an indirect measure of autonomy. And then we can say that evolution will tend to information with higher life ratios, because information that has higher life ratio will be better fit to propagate itself. In other words, we can expect life in the universe. It's not something that was, let's say, that we got lucky in our planet with Goldilocks conditions. I mean, these Goldilocks conditions, it refers to the fairy tale with Goldilocks and the three bears. So there's like the chair that is too small and the chair that is too big, and then the chair that is just right, and the soup that is too hot and the soup that is too cold and the soup that is just right, and the bed that is too hard and the bed that is too soft and the bed that is just right. So many conditions in our planet are also just right. So the distance from the sun, the atmosphere, the gravity, the composition, many things are just right. And if you vary them a bit, then life would not be viable. Also, the constants of physics, Planck's constant, the gravitational constant, and so on, people say that if you vary them slightly, then life wouldn't be viable. So that's the so-called fine-tuning problem in cosmology. But then these Goldilocks conditions, some people say that life is very difficult to find because then you need all these conditions. And of course, we are here and we can tell the tale about it, but it will be very difficult to find it in the universe. And what we are suggesting with this is that that is not the case, that we can expect life in the universe and in other solar systems, and perhaps not only in planets or moons, but in other contexts, simply because information will tend to evolve higher life ratios. And information can be, of course, in molecular systems, but not only. Of course, how do we interact with other types of living systems that are, let's say, not based on carbon and DNA? That's a different question. How do we even detect those types of extraterrestrial life? It's a huge open question, but that's what the field of astrobiology is busy with. There's some interesting work by Sarah Mary Walker in this direction. How can you detect thousands or millions of light years away potential of life in different planets? And then about cognition, we can very generally say that a system is cognitive if it knows something. So then we can say that all agents are cognitive since they know how to act on their environment. So again, there's no boundary between non-cognitive and cognitive systems. So there's just more or less cognitive or different types of cognition: human, animal, plant, bacterial, immune, biological, adaptive, systemic, artificial. And then again, in evolution, there will be a tendency to increase complexity of cognition because of all the laws that we derive. So again, if humans were not around, would other species evolve cognition that is comparable to ours? Very probably yes, and very probably they will after our species is no longer here for whatever reason. And actually, a few years ago, there was a preprint on the archive. I forget. Yeah, it's called the Silurian hypothesis. So it's about the question whether dinosaurs, I don't know, 30, 50 million years ago, developed a civilization, perhaps not as complex as the one we have now, but let's say it's something complex enough that they had language and cities, perhaps, and agriculture. Let's say a high level of cognition that is, yeah, perhaps not global warming and satellites and spaceships and skyscrapers and so on, airplanes and atomic bombs, but let's say something that would be, let's say, perhaps even just Paleolithic intelligence. And the authors were not in favor of this hypothesis. They would say, like, well, this sounds ridiculous. I mean, to have like dinosaurs with clothes or with tools, there's no evidence about it. But then they were basically trying to disprove that hypothesis, and the conclusion is that it was very difficult with the given evidence, because the amount of fossils that we have is such that basically we have, on average, one fossil every 10,000 years that is dinosaurs were on Earth. So if you had a little window of 2,000 years of dinosaur civilization, sorry, let me close the window because there's some scandal going on in the parking lot. So if there was a tiny 1,000, 2,000-year-old window where there was some civilization and then for whatever reason they disappeared, very probably we wouldn't know about them because they didn't live, well, if it's so difficult to go into archaeological sites that have just a few thousand years old or even a few hundred years old, the decay after millions of years is such that it's very probable that, let's say, there would be no remains of whatever construction or nests or houses they might have. So again, it's not that there was this Silurian civilization, but it's difficult to say that there wasn't. And in a similar way, we might wonder whether in a few million years, if, say, another civilization arises, will there still be something from our civilization left? Maybe yes. I mean, we have polluted so much the planet that probably there will be some Pepsi cans and diapers and so on popping up in a few million years. But yeah, it's difficult to know. But anyway, returning to the topic, we can say that in evolution, there's a push for an increase in the complexity of cognition. And this can also guide the discussions about what might be the future of our species and of our planet, because if we have an increase in organization, an increase in scales, many people speak about internet as a global brain, whether it will acquire consciousness or not. Of course, this is already speculating a lot, but let's say the cognition of our species, I mean, of our individually, we're increasing our cognition thanks to our technology. And then we might doubt whether the cognition of our species is increasing or not. But let's say many people wonder whether we will make, or we already made, another metasystem transition towards a higher scale of organization. And in a sense, we did already, because we cannot survive as individuals separated from our civilization. Not only that, but let's say our Paleolithic ancestors would have a difficult time surviving on their own if they were not in bands, even nomadic bands, or in villages. I mean, those were already higher scales of organization of simple human societies. So I think we have been having such transitions, only that it's similar to the question whether a cell in our body would be aware that they are part of our body or not. Or would they be aware that we have consciousness as an organism or not? And of course, it's difficult to speak what's consciousness and whether there could be a social consciousness or a global consciousness. But what we can see and we can measure is that the organization at the global level seems to be increasing, or at least the complexity seems to be increasing. And then there might be limits to that complexity given by the boundaries of our planet. So science fiction writers imagine situations or scenarios where, let's say, we go beyond our planet and start expanding to other planets and to other solar systems. And right now it might seem like too futuristic or ambitious, or also, why do we want to go to Mars if we can solve the problems in our own planet? It's better invest in reducing poverty, or I mean, there are so many things that we could try to solve before going to Mars. Well, my answer to that is that it's easier to go to Mars than to reduce inequality. But anyway, one of my colleagues, Clement Vidal in Brussels, he takes these ideas further, and he quotes one science fiction author that has a classification of the advances of different civilizations by the amount of energy they use. So our civilization, let's say, each revolution has also come with an increase in the amount of energy that we harness. So the agricultural revolution kind of gathers, I don't know how much energy, but a lot of energy, with different waterworks, hydraulic projects with dams, with canals, and so on. The Industrial Revolution, and more recently the oil, gasoline, gas, and so on, have increased a lot the amount of energy that we harness, and more recently alternative sources of energy, nuclear, solar, and so on. But let's say we're having problems with sustainability because our demand for energy increases faster than the sustainable sources of energy are increasing. So this tendency continues, then we won't have enough energy in our planet to satisfy our needs. So where will we get our energy from? Well, from stars. So there's this idea of stellivore civilizations that basically harness or basically suck the energy directly from stars. And there's some celestial objects that seem to be like there's something that it's sucking energy out of a star. So there's this idea that these are these stellivore civilizations that are highly advanced, and we might reach that technology in who knows where. But anyway, that would be in concordance with this narrative that there's an increase in complexity, and let's say there is, whether it's feasible or not in our solar system, that's a different question. Whether our species will survive for a few more 100 years or not, that's another question. But let's say at the universe level, let's say there is a tendency of increasing complexity. So there are plenty of things that one can do to try to formalize and explore this loss of information with simulations. Something we already began doing is to address the question of downward causation a bit more precisely, to describe thermodynamics in terms of information, also what I mentioned about economy as non-conserved information dynamics. Also, we could relate this to game theory, where you have non-zero sum games. Its relationship to philosophy and ethics. There's some of that we have worked on. Also relating it with Buddhist philosophy, where information, in other words, the object, the agent perceiving it, the subject, and the action of perceiving or meaning making are part of the same totality, and therefore you cannot separate them. So, I mean, there are plenty of things to continue working on. So just to conclude, these were tentative laws to describe evolution at all scales. And again, this is epistemology, not ontology. Different descriptions can be used for different purposes. And quoting von Bayer, we can use information as common languages across scientific disciplines. And the paper, which was published as a book chapter, it's available there. I'll also put it on the Google Classroom. So for the next classes, there will be project advances. I still have to see whether before or after the Easter break, probably before the Easter break, it will be good so that you present your advances, so that, let's say, you can take advantage of Easter week to advance even more in your project. And we'll see introductions to network science, to computational social science, and to artificial life. Okay, so are there any questions?
No, no one.
So I don't think that everything was completely clear, so probably it's the opposite. Yes, Elio?
Oh, thank you. I was thinking thinking as example in three basic paradigms: the determinist, stochastic, and chaos. what is the role of information in these three kinds of systems?
Yes. Yeah, that's a good question, because already, like in the early 20th century, it was a big debate in physics whether the universe was deterministic or not. I mean, let's say the Copenhagen school was saying, no, it's not deterministic because of indeterminacy principle, Heisenberg's principle. And Einstein would say, no, God doesn't play dice. And this is a question on, this question assumes that there's like a basic level of reality. And then the question tried to answer whether at that level, the laws were deterministic or not. And from this perspective, there is no basic law level of reality, because information is not at a specific scale, but at all scales. And what we can see, I mean, this is already from computer science, that there are computational equivalences, and you can see that, let's say, you can have a deterministic system that approximates as much as you want a stochastic or chaotic system. And you can start also with a stochastic or chaotic system and approximate as much as you want a deterministic system. So at the end, it doesn't really matter. I mean, pragmatically, it doesn't matter whether reality is or not deterministic. You can have undeterminism, unstochasticity, and chaos independently of that, starting with whatever you want. So it doesn't mean that they're the same, but if you have one, you can get the other one. So in other words, in terms of information, we don't care. And this is related to Lucrezia's question: how is uncertainty in agent behavior handled? I mean, this is a common question that, let's say, has been studied more theoretically, but also in biology, because, let's say, animals have certain uncertainty of their environment, and then they need to make decisions. And there are different theories on how they handle this uncertainty. So one is the Bayesian approach. Basically, they kind of make educated guesses on what's the most probable future, and based on that, they make decisions, and sometimes they are right, and in some cases they are mistaken. So, I mean, that's like one type of handling uncertainty, but I guess that evolution will come up with different strategies for handling uncertainty in different ways. So it will be difficult to say that it's handled in a single way. So what we have seen is that, I mean, at some point we mentioned three main approaches for dealing with complexity: anticipation, adaptation, and robustness. So each of these could be seen as a way of handling uncertainty as well, in the sense that if you can anticipate uncertainty, then you're good. But if you can't, then you can either adapt to it, or you can be robust towards it, or you can be both and try to balance. So yeah, those would be like very general ways in which uncertainty can be handled to preserve the information of the agent. So the law of information organization, basically, when you have agents producing their own information and their own constraints, that kind of ensures or limits the transfer of variety from the environment to the agent, and that reduces the effect of uncertainty and also promotes the propagation of the information within the agent. So it's like a very general way of speaking about survival that can be applied to living systems, but not only to living systems, but to information in general. Sophia asks, is the speed of... Yep. Sophia asks, is the speed of life a limit to information propagation? Speed of light or the speed of light? Okay.
Light, I meant like.
Yeah. No, but actually, the speed of light sounds interesting. We should try to explore whether that there's a limit to the speed of light. Yes, it is a limit, and also well, you can see that many of these tentative laws are not only tautologies, but they are very vague. So this law of information propagation that says that information propagates as fast as possible. What is this as fast as possible? You might ask. So it's this balance between transformation and propagation that will be limited by a specific context. So I would say that the speed of light does impose a limit on information propagation, but also there's this question that I haven't been able to answer. So assume that in different parts of the universe, the same computation takes place. So in different parts of the universe, you get the same information produced or the same information propagated. Does that mean that information was transmitted or not? So I would say that no, but then if you make measurements in both places and you get the same result, then you say, hey, there's correlation, spooky action at a distance. So I mean, I wouldn't be able to give a precise answer about that, whether that constitutes information propagation or information transmission, or just that is the same process occurring in different parts of the universe. But then if the same information is propagating in different parts, yeah. I mean, and independently on whether they have, let's say, a common ancestor or not, at some point, let's say, we assume that they came from the Big Bang, so mainly they have the similar trajectories, but then does that information propagation kind of can be traced back to the Big Bang and then, let's say, to the past and to the future again, back to the present, or not? I don't know. But yeah, I mean, in the traditional sense of getting some information from one place and transmitting it to another, yes, light sets a bound. In thermodynamics, there have been, well, there's this Landauer principle, and there's like a thermodynamic limit on the energy you require to erase information. So there are some things that, let's say, start to emerge that could give us better insights on what are the limits of information propagation and transformation and so on. Because very probably we can also speak about the limits of computation, in the sense that if you are computing, I don't know, some algorithm or whatever calculation in a physical computer, then you can say, well, the maximum speed is this. But then is there a theoretical limit of how fast could computation occur, let's say, given the constraints of physics? Probably you could, but I have no idea how to start. So that's another open question.
I have another question.
Yes.
How do you know how far got the information? As example, in my case, I'm interested in the annual hurricane activity. How I know how far, how many years ahead the actual situations give an impact, transmit is relevant? How far is relevant?
Yeah, you can check this with either with perturbations or with correlations. So let's say if you have a kind of model that can reproduce your data properly, or let's say with a high degree of precision, then you could say, okay, I have this trajectory, and then we'll go to the past and say, okay, what happens if we change, let's say, 2 degrees for 1 day in this year? And then you run the simulation again, and then you see how much it changes. So like that, you can see like the horizon of how fast the different trajectories diverge. And this will tell you how much history you require for a specific precision that you want. So it's a bit similar to weather forecast.
Thank you. Yeah, I know that the Liverpool
Yes, Amaury.
Well, it was a tremendous lecture, Professor. Thank you very much for sharing this knowledge with us. It was not just inspiring, but also very gratifying. I think this will be my favorite class along the course. And as a final comment, a couple of days ago, Sarah Walker gave a lecture on extraterrestrial life. And if you are interested in this kind of topics, you can find it on the Santa Fe Institute YouTube channel.
Yes. Yes, Sarah has been working with different ideas related to astrobiology already for several years. She's at the Arizona State University and also Santa Fe Institute. Yeah. Yeah, so last time I spoke with her, I forget, well, at some meeting, well, we were speaking about how to detect life in other planets when you just have like I mean, you can derive some properties about the atmosphere from the light that we receive from those planets, and not much more. And the problem is that there are many complex atmospheres that can be produced by abiotic processes, chemical processes. So what she was telling me is that it's difficult to discern which ones are like really, okay, this has to be generated by life because this, I don't know, which complex molecule is generated by living systems. Because also, let's say, the complex molecules are not stable in the atmosphere, so they degrade. So even when you have life, like on Earth, majority of molecules in the atmosphere are say, nitrogen and oxygen and so on, ozone and so on. So whether you detect traces of methane or ammonia or some other a bit more complex molecules, that could be produced by abiotic processes or by biological processes. So she was telling me that they are rather than having a yes or no criterion, like trying to work with probabilities, in the sense that there's a very high probability that the atmosphere of this planet is not generated by living systems, or there's a high probability that you have living systems in this atmosphere because of the complexity of the molecules, but we are not sure unless we send a mission there. This reminds me of an anecdote of the 1960s during the the Cold War and the space race between the Soviet Union and the United States. So there was the Soviet space program, if you recall. They sent the first satellite, the first cosmonaut, also the first dog to the cosmos. So they were ahead of the United States in the early 60s. And Kennedy told, no, we'll reach the moon by the end of this decade, and they did. And the it's a somewhere in between. There was a mission, let's say, unmanned mission to the moon from the Soviet Union. And they wanted to check different things, but they realized that the load was too heavy because, of course, it takes lots of energy every kilo that you send into orbit. So the director of the space program, Soviet space program, had to slash one of the instruments that were going to be sent to the moon. So he decided to scrape an instrument that was supposed to check whether there was life on the moon. Still in the late 19th century, in scientific journals, they were publishing papers about what they were thinking they were seeing in the moon with the telescopes they had then. And they were assuming that they were Martians, and let's say there were supposedly these channels that Percival Lowell detected, and let's say they assumed that it was a Martian civilization. And also there were some people saying that in the moon there was some vegetation. Anyway, getting back to the Soviet program. So this device that was supposed to detect whether there was life on the moon or not was scraped. And then the director of that project, of course, he was enraged because I don't know how many years they were working on that. So he stormed into the office of the space program director and was like, "Oh, comrade, you don't know what you're doing. This is the most important project. It will change how we perceive our place in the universe and so on. How can you do this? You have to reconsider this. It's the most important." And very calmly, the director of the space program kind of lets him vent and says, "Well, you see, comrade, I took your instrument and left it overnight in the parking lot. And in the morning it said, there's no life in this planet." So it was an easy choice. And then, of course, the director of the project couldn't argue anything. So if it's difficult to detect life in our own planet, then imagine trying to do it light years away. Which would be like an interesting question. Okay, if you were detecting Earth from the distance, how could you tell there was life? And I mean, not intelligence, but life. Because some people say, well, you check for the electromagnetic waves and you will see that. Well, if you watch or read Contact, then you know what I'm speaking about. Okay, so so we have how many weeks before the holidays? Two weeks before the holidays. So next week we'll have more classes, and then the week after that, which is the 1st of April, we'll see the advances in your projects, and then we'll have the spring break, and then we'll continue second half of April. So next week, if you can come to the Centro de Ciencias de la Complejidad, I'll see you there at 10. And if not, I'll see you here. Have a good weekend.
Thank you. See you on Tuesday.
Thank you.
Thank you, Professor.